Our project is named the World Model. This is based on a proposition by Prof.Yann. The proposed architecture tries to mimic the human brain. We as humans extract features from the world using our eyes and pass it to the other parts of the brain. In this architecture also, the perception module extracts information from the world which an AGI agent would need and passes it to the other modules. It should be able to extract a set of generalized features which the remaining modules can use. So what are these generalized set of features that could be useful for an AGI? It will need to know what is in its view, that means the content information. Then it will need to know where the objects are moving. This can be extracted using optical flow features. Then it needs to know the relative positions of the objects and the structure. This can be extracted using depth features. Then the next question would be how to train such a model. For this, Prof.Yann LeCun proposes the JEPA architecture. The JEPA architecture avoids loss calculation at pixel level and calculates loss in latent space. So why is that required? If we consider an image like this and blur the ears, a vision model should be able to understand that this area has ears. But it is impossible to predict the exact position and angle of the ears. It can be like this, or even like this. Therefore, it is not required to do loss calculation at pixel space. So how does this training architecture work? Given two consecutive frames x and y, send it through the encoder and get a latent representation sx and sy for the two frames. Then send sx through the predictor network. With the help of a latent variable z, we can get the predicted latent representation of y, s hat y. Finally, we calculate the loss in latent space using sy and s hat y. So this is the proposed model and the training architecture. This is a fully self-supervised training setup. We have a single shared encoder and two task-specific decoders. In each iteration, we sample a batch from the content dataset and create two augmented views from it. Then we feed it to the encoder and get its representations, and then feed that representations through the content decoder. For the final output embeddings, we calculate the loss using the Vickers constraint. For optical flow and depth, we sample 3 consecutive frames from a monocular video and feed to our encoder. The representations of these frames are then fed to the flow and depth shared split decoder, and we extract optical flow and depth maps. For optical flow and depth, we use SSL flow and depth constraints. These are the results of our model. As the benchmark, we use the self-supervised multi-frame monocular scene flow model, which is the 2021 CVPR paper, and is on a similar line of research. As you can see, on 5 of the 7 considered metrics, we have surpassed the benchmark model. And this is the result of a real-time inference done at the university premises. You can see the flow maps and the depth maps. And this is the result of an inference done in a challenging indoor setup. Also, our model generalizes well on downstream tasks, like segmentation. You can see the segmentation maps here. And this is a demonstration of the flow and depth maps generated on the Kitty dataset using our model.